In the previous example, everything was very smooth in the sense that we could easily derive the posterior distribution of the parameter P, which turned out to be beta, and we could then apply very nice formulas to compute the posterior mean of this beta distribution, or to compute the probability that ultimately these formulas come from solving certain integrals. So for instance, we could compute the posterior means because we arrived at the closed form, so equation 9, which results from solving this integral. We could also compute the probability that candidate A wins, also coming from this integral. This is very nice. Now, in many, I would say in most interesting social science problems, we are either not be able to solve these integrals, or not be able to summarize the posterior distribution using standard closed form known formulas. And here's where modern Bayesian computation methods come handy. And the idea is, well, when we are not able to solve these integrals, what a Bayesian does is to resort to simulations, right? And in particular, we resort to what's known in modern Bayesian computation of Markov chain Monte Carlo simulation. In the slides, I give a little bit of detail about how, why these Markov chain Monte Carlo simulations are called the way they are. But essentially, the idea is that when I cannot come up with closed form solutions for the parameters of quantities of interest of the parameters, I can generate simulations. Now, and the two key algorithms, and they're kind of very different. There are many different or potential ways to simulate values of the parameters that are amenable to then be summarized or draw inferences about these parameters. In modern Bayesian computation, there are two key algorithms that we use. One is the Gibbs Sampler, and the second one is the Metropolis-Hastings algorithm. And the idea is we resort to these simulation techniques, in a nutshell, because we have models for which it's difficult or impossible to come up with closed form solutions for the parameters, when there are no known formulas we can use to obtain their posterior mean or median or variance. However, we can use Monte Carlo simulation techniques, or Markov chain Monte Carlo simulations, to that will enable us to draw inference about these parameters, even when we don't have closed form solutions. So let me tell you in a nutshell what these two key approaches to Bayesian simulation, or to these two main algorithms, the Gibbs Sampler and Metropolis-Hastings algorithm, what they do. And essentially, the idea is the Gibbs Sampler is the most basic algorithm used in modern Bayesian computation. And it is applied when I have a model with several parameters. Think of any interesting model, a probit or logit. And these parameters have a joint posterior distribution of all the parameters. That's very difficult to draw samples from. But we can split this joint posterior distribution in a series of conditional posterior distributions, and we can sample from these conditional posteriors. This is kind of what the Gibbs Sampler does. Break down the problem of generating samples of the parameters via simulation, because I cannot simulate from the joint posterior distribution. But if I break down the problem into a series of conditional distributions, I may then be able to simulate. And the Metropolis-Hastings algorithm is a generalization of the Gibbs Sampler that we are going to apply when even this approach of breaking down the joint posterior distribution of the parameters into a series of simple conditional distribution doesn't work. So Let me illustrate each of these two key or main Bayesian algorithms. They're the basis of modern Bayesian computing. As I said, suppose I have a vector of parameters, big theta, and within big theta I have k parameters. Okay, so suppose that the joint posterior distribution of the parameters has a very complicated form. There's no closed form solution for these parameters, and I cannot even simulate from this joint posterior distribution. However, I can break down the problem or split the joint posterior distribution into a series of conditionals. So I can suppose the conditional distribution of theta1 given the rest of the parameters is something I can recognize. The same for the conditional distribution of the second parameter given all the other parameters and the data, of course. And the same for the conditional posterior distribution of theta k given theta1, theta2, etc. If each of these conditionals are recognizable, or in other words, I can generate samples from these parameters, from these distributions, there is a version of the law of the large numbers, which I go into a little bit more detail in the slides, that tells me, well, if this works, if I can break down this problem into a series of conditional distributions, I can sample from each of them, and then I can approximate the joint distribution of all the parameters. So essentially, what the Gibbs sampler does is, starting from some initial value of the parameters, if I have a problem with many parameters, I break down this joint posterior distribution from all the parameters into a series of conditional distributions, each of which is recognizable, meaning I can sample, generate draws from each of these conditional, and if I repeatedly sample from each of these conditional distributions, I will approximate the stationary distribution of the parameters, equilibrium distribution of the parameters. Let me give an example in practice. So suppose I have a simple, a random sample from a normal distribution where I do not know the mean, mu, and the variance, sigma squared, of this distribution. And the goal of this exercise is to estimate mu and sigma squared, or to be Bayesian, to derive the posterior distribution of mu and sigma squared. And again, in this exercise, I'm going to resort to the Bayesian mantra. The posterior is proportional to the likelihood times the prior, right? So this is what equation 18 there says. The posterior distribution of mu and sigma squared, given the data, is proportional to the probability distribution of the data times the prior distribution of the parameters. Okay, so again, we're going to go through the 4 steps of Bayesian inference, but applied to this exercise. Since we said that we have a sample taken from a normal distribution, the sampling distribution of the data is given by equation 19. So the posterior distribution of the parameters is going to be, like you can see in equation 20, a normal likelihood times the prior distribution of the parameters. The second step, any Bayesian analysis, is coming up with the priors for the parameters, mu and sigma. I could generate a joint prior, so essentially generating a prior distribution that's together for mu and sigma squared. It's easier, typically, though, to use different priors for different sets of parameters. In this case, to specify a prior for mu and a different prior for sigma squared. So we can choose what we mentioned, we call conjugate priors. So priors such that the posteriors are going to be of the same family of mean distribution than the priors. So it turns out that for the mean of a normal distribution, the conjugate prior is the normal. For the variance of a normal distribution, the conjugate prior is the inverse gamma distribution. Okay, so point is, once I have that, once I choose a normal prior for mu and an inverse gamma, like the one we see in equation 23 for sigma squared, I can then move on to step 3, which is deriving the posterior distribution of the parameters. Okay, so let's do that. I have the data likelihood, I have the prior for mu, I have the prior for sigma squared, and applying the Bayesian mantra, posterior is proportional to data times priors, I arrive at equation 24. The problem there is that equation 24 is not something I can recognize, right? It's a equation that doesn't have a very clear-cut or closed-form solution. So, in other ways, I cannot analytically solve this equation. It's also impossible to simulate from this equation. And this is, however, when the Gibbs sampler comes in handy. Because what does the Gibbs sampler do? Well, we said break down this problem of deriving the joint posterior distribution of the parameters into a series of conditional distribution. Another way of saying it in this example is, well, when I want to derive the conditional posterior distribution of mu, let's take sigma squared, the other parameter, as a constant. And when I want to derive the posterior distribution of sigma squared, I will take mu as constant. And then I just repeatedly sample from these conditional distributions. And by doing so, I approximate their joint posterior distribution. So to derive their conditional posterior distribution of mu, what I do is take sigma squared. I have two parameters in this exercise. So this is a special example of the equation, the more general formulation of the Gibbs sampler. Here I have k parameters. Well, in this particular case, I have two parameters, mu and sigma squared. And what I do is I derive the conditional distribution of mu, taking sigma squared as given. So in other words, take any term in this joint posterior distribution that doesn't depend on mu as a constant. Okay? So essentially, I can forget for a moment about all the terms that do not depend on mu. And with a little bit of algebra, I arrive at the fact that, and again, this is the slides go into much more detail about this, but the point is, if I take sigma squared constant, when I derive the posterior distribution of mu, and I do a little bit of algebra, what I arrive at is a equation like 26, where the conditional posterior distribution of mu resembles a normal distribution. Equation 26 looks like the kernel of a normal distribution with a certain mean and a certain variance, right? It's a normal with mean given in equation 28 and variance given by equation 29. And this, I know how to generate values from a normal. I know how to compute means, variance from a normal, and I can simulate very easily in R using the command rnorm to generate values from a normal distribution. Right? Similarly, when I derive the conditional posterior distribution of sigma squared, I treat all the terms that do not depend on sigma squared as constant, and again doing a little bit of algebra, what I arrived is at the question 31, which is the kernel of an inverse gamma distribution. Okay, again, I do know how to generate samples from an inverse gamma using a command such as rgamma in R. The point is that starting from a joint posterior distribution that was very complicated, let me go back and show you. This was the joint posterior distribution. I had no idea what this is. Is this a normal? This is a no. Is this an inverse gamma? No, this is a complicated equation. I have no idea how to compute posterior means, posterior variances, how to summarize the parameters. Okay, so what I did is I broke down this problem of deriving the joint posterior distribution of the parameters into a series of conditional distributions. And once I do that, I arrived at a problem in which I end up with a normal distribution and an inverse gamma distribution, and those I know how to work with, right? So essentially, the way in which the Gibbs sampler would work in my problem would be start with initial values for sigma square and mu, choose a normal prior for mu, an inverse gamma prior for sigma square, and then repeatedly draw samples for mu out of a normal conditional distribution, for sigma square out of an inverse gamma distribution, and that will approximate the joint posterior distribution of the two parameters. You have a script that comes together with these slides called Gibbs Sampling normal distribution, in which essentially I show you how to, starting from initial values of the parameters sigma squared and mu, I start drawing samples. And as you can see, I start drawing, for instance, in this figure, what I see is that I can start generating samples for mu out of a normal distribution. Originally, the values of the normal are kind of all over the place, but pretty quickly they stabilize around a value of 2. They reach their equilibrium. So the posterior mean, the value of mu is going to be centered around 2. Similarly, for sigma squared, I start generating samples from an inverse gamma, and at the beginning, the samples generated are going to be all over the place, but eventually they will stabilize around a value close to 4. And this is kind of, in a nutshell, what the Gibbs sampling does: break down a complicated problem into a series of easier conditional problems, and under very general conditions that hold under for most social science problems, doing this trick of simulating the value of one parameter, taking the value of the other parameter as given, and going back and doing this many times, ultimately leads me to the stationary distribution, the posterior distribution of both parameters. Essentially, I reach I approximate the joint conditional posterior of all the parameters by doing this trick of breaking down the problem into a series of conditionals.